Good morning, afternoon, or evening. Welcome back to some more stats. Today we're going to be working mainly with probability. Like I mentioned in the last video, we're going to completely get rid of everything else that we have previously worked on and do something totally different. Probability, in this specific course, we'll be working with three main topics: basic probability concepts, basic probability rules, and counting. So let's start off with the very first topic, basic probability concepts. So what do we mean with probability? What are we working with? And how do we write it and stuff like that? Well, let's see. Here we go. So here are a couple definitions that we use typically when talking about probability. The very first thing is an event, is just any collection of results or outcomes of a procedure. Like for example, you just roll a pair of dice. Once you roll them, many different things can happen. So, yeah. An event can be further broken down into a simple event. This simple event then cannot be further broken down into simpler components. It's as far as we go. So for example, like rolling an individual die, and then the simple event would be roll a 1. Or say that we say the probability of rolling an even number. Well, an even number could be a 2, 4, or a 6. So the 2, 4, 6 are the further broken down events. Those are the simple events. And our sample space consists of all possible simple events. So everything that could happen when rolling a pair of dice or when doing some other kind of simulation or procedure. The way we write probabilities, if you take a look down there, it's P of A. It's similar, well, it's actually the same thing as function notation from back in algebra. So we read it P of A. What it really means is the probability of event A occurring. And then the bottom one, P of A, but with the bar on top. That means the probability of A not occurring. This is what we call a complement event. Later on, we'll see the formula for it and how to use it. It's pretty neat. And once we found a probability, we need to write it in a specific way. We can either use a simplified exact fraction, or if that fraction turns into an exact decimal, so it doesn't keep on repeating, it just stops at a nice point. And the third option is to use a rounded decimal up to 3 significant digits. So if our decimal keeps going and going and going forever and ever, we just cut it off at 3 significant figures. Okay, so now there's a very specific range in which probabilities occur. All probabilities fall between 0 and 1, inclusively. So what does that mean? We got a little number line here. So we've got 0 on the left, 0.5 in the middle, and a 1 on the right. All probabilities fall within this range, and only this range. It could be, a probability could be 0, it could be anything in between 0, 0.5, and then anything between 0.5 and 1, and it could also be 1. And that's where probabilities reside only. A probability of 0 means that that event is just completely impossible. It cannot happen no matter what. A probability of 0.5 means a 50% chance, so could happen, could not. Like right exactly at the middle. And a probability of 1 means that that event is certain. There's an absolute guarantee that it's gonna happen. So from this range, we can then conclude the following. There are no negative probabilities and no probabilities greater than 1. So from this little number line, we can't have anything lower than 0. We can't have a probability of negative 0.17. That's just can't happen. We can also not have probabilities greater than 1. So like a probability of 1.57, no. It's only going to be between these. And this is a fairly important topic. So yeah, this is important to remember. There are 3 main ways that we approach probability. The very first one is the relative frequency approximation. Sometimes it's called the experimental approach. So here's how we find it. It's the probability of A is the number of times A occurred out of the number of times the procedure is repeated. So here's where a simulation is used. So if we want to find the probability of flipping a heads, well, we can always flip the coin over and over and over. But after a couple of minutes, we're going to get tired and bored and annoyed. So typically software is used here, some kind of program to simulate coin flipping and stuff like that. The only thing though, when doing the experimental approach, you need to keep the law of large numbers in mind. So this law tells us that the relative frequency gets closer to the true probability the more times a procedure is repeated, hundreds and thousands of times. So if you are to use the experimental approach, you need to repeat that procedure for thousands and thousands of times. And only then can you reach a good probability or a good approximation of the true probability. So yeah, software is, like I mentioned, a good item to use there. The second approach is the classical approach, also known as theoretical. So P of A is the number of ways A can occur out of the number of different simple events, or out of our entire sample size. This one's a little more common than the experimental. In fact, in class, or at least in the practice problems that I'll show, we'll be using this one, not so much the experimental. And then the third one is kind of interesting, a subjective probability. P of A is estimated using knowledge of the relevant circumstances. So based on perhaps some past data or some other kind of knowledge, we can kind of guess what a probability is. It's not the most exact, but I mean, if we're in a pickle, then yeah, we can try the third one. The rare event rule. All right. So this one's kind of interesting. It's a mouthful, but it is a pretty important topic. If, under a given assumption, the probability of an event is very small, and that event occurs significantly less than or significantly more than what we usually expect, then our original assumption is probably not correct. So if we believe certain claim, but then that claim happens way too often or not often enough after running, I guess, some kind of procedure, then that claim is probably not correct. So here at the bottom, we have a little more kind of formula looking type thing or rule. So X is a significantly high number of successes if the probability of X or more is less than or equal to 0.05. And also, X is a significantly low number of successes if the probability of X or less is also less than or equal to 0.05. And right here, this is a pretty important topic. It will be very useful once we get into hypotheses testing, or that's where we'll actually be using it. But that's later on, so just make a little note of this guy. Odds are usually used in casino games, so in betting and probabilities of winning or losing and stuff like that. There are some pretty cool practice problems you can use with odds. In our case, I'm gonna go ahead and not dedicate too much time to it. It is fairly interesting, but I don't see it being too important. So at least these are the formulas there. I won't be covering how to use them, but at least now you know them, but we won't be seeing them too much. Disjoint events, also called mutually exclusive events. So if we have events A and B, then they're disjoint or mutually exclusive if they cannot occur at the same time. So if you look at this little diagram here, we got event A and event B. And there is no overlap between those two. They're just separate, they're their own thing, they're minding their own business. So those are disjoint events. They cannot happen at the same time. It's just either one or the other. And that's it. Independent versus dependent. Also in parentheses I got with replacement and without replacement. So what is all this stuff about? So events A and B are independent if the occurrence of one event doesn't affect the probability of the other event. Otherwise, then they're dependent. So if we take a look at the picture here, we got some cards, right? So a standard deck of cards has 52 decks and 4 suits, 13 cards, and all that jazz. Now, if we take out one card from the deck, and now we have 51 cards left in the deck, right? So the probability of picking any other card will change because we have fewer cards now. So in this case, picking cards will be a dependent event. It is picking out one card is affecting the probability of the rest of the cards. The dice, however, they don't really care. You just roll a dice and you roll a 6, and that doesn't change anything. You can still roll another 6, you can roll a 5, a 4, or any number on the die. So yeah, rolling dice are independent. They don't change the probability of any other event. Taking cards out of a deck without replacing them or without putting them back in, yeah, that's dependent. There's a way to get around this though. The second little bullet here says, when sampling with replacement, selections are independent events. And when sampling without replacement, selections are dependent. So with the cards, say we just randomly shuffle them and we take out a card and it's a 2 of hearts. Cool. So we've got the 1 card outside and we got the 51 inside. But if we put that card back in the deck, we once more have 52 cards in total. So now the probability of picking another card is not going to change because there's the 52 cards right there. So now, sampling with replacement, putting it back in, leads to independent events. We aren't switching any probabilities anymore. So that's kind of neat. And then the very last bullet point here is the 5% guideline for cumbersome calculations. When sampling without replacement, and the sample size is no more than 5% of the population size, then we can treat the selections as being independent. And notice how it says treat. The events will not be independent by nature, right? But we can treat them as they are. So we can get around dependent and independent and all that weird stuff going on by just keeping those kind of parameters in mind. Sample size is no more than 5% of the population size, and without replacement. So we finished talking about the concepts, so definitions and some key ideas for probability. Now, how do we calculate probabilities? That's the fun part, right? The actual math section. Well, let's go. So the very first rule, or set of rules that I want to talk about, are the complementary rules. And we're going to throw in the probability of at least one into the mix as well. So the complementary rules, as I mentioned before, a complement is a probability of one event not happening, right? So the formulas here, they're essentially the same, even though there are three formulas, they're basically doing the same thing. So if we add a probability plus its complement, then we get a 1. And then we can subtract either one, and we'll get the remaining probability that we want to find. So probability of A not happening is 1 minus the probability of A happening. And also the other way around. Probability of A happening is 1 minus the probability of A not happening. In fact, we got a picture here. So this is event A. So that would be the probability of A happening. And then A not happening would be the rest of the space, which is in orange, which is also the complementary color of blue. So yeah, complementary colors are cool. Now we can expand the complementary rules and also add a little bit to it. That's where the probability of at least one comes into play. So the probability of at least one A, or at least one occurrence of event A, is equal to 1 minus the probability of no occurrences for event A. So essentially it's the exact same thing as the complementary rule, but now it's a little more applied. It's more specific towards an event. There are other ways that books like to write complementary events. Some use a little apostrophe, so A prime. Some use the C up top, kind of like where the exponent goes. You can see either of these. You can use any one you want, or just stick to the one your book has. The bar is, I think, the more common one. I've seen that a lot more, so I'll be using that one. The second rule we got here is the formal addition rule. So if we have the probability of A happening or B happening, the formula states that it's the probability of A plus the probability of B minus the probability of A and B. So once more, we take a look at this little diagram. So the probability of A happening or the probability of B happening, and we kind of just get rid of the overlap in between. So that's essentially what we're doing. Now, if our events are disjoint or mutually exclusive, if you remember, then that means that there is no overlap. So then you would just add up the two probabilities, and we won't have any subtraction to do because there's no overlap. Another way that I've seen books write an or the addition rule problem is with the little U there. So P of A and then that U symbol. It means a union. So from set notation, sometimes books use that notation. So yeah, use whichever your book uses. And the addition rule is typically used when randomly selecting one single subject or an item. So when you're working on a problem, it says find the probability of if we randomly select one person or one thing. That's kind of a little hint that we may use the addition rule. The multiplication rule. All right. So now we have P of A and B. That's equal to the probability of A times the probability of B given that A has already happened. So that's what that vertical line means there. It's basically saying given that, and then that this event has already happened. So probability of B given that A has already happened. So we just multiply those two. So now in this case, we're not so much worrying about A or B. Now we only really care about the middle section. That's where the cool stuff is at. If we have disjoint events and there is no overlap, well, we just multiply the probabilities together and we call it a day. The other notation used for the multiplication rule is with the upside down U, or intersection. So you can see that kind of notation flying around in nature as well. Now the multiplication rule is typically used when randomly selecting two or more subjects or items. So if you see that in your practice problem or homework or whatever, it's a little hint that we'll have to maybe use the multiplication rule. Conditional probability. So here's that same symbol as before. The probability of B given that A has already happened. So to find that, we just need to find the probability of A and B and divide by the probability of A. So in essence, we've got our two events here. We're gonna get their intersection right there in the middle, and then just divide by the event A. This one's a little weird to wrap your head around, especially, I don't think the diagram helps too much, but it looks cool. And also a very big thing to keep in mind, the probability of B given A is not the same thing as the probability of A given B. So you can't just flip those two willy-nilly. They're not going to be the same, they are completely different. So please watch out and don't make this mistake. Alright, so now the fun begins. Let's apply all of these rules and solve some problems. How does that sound? It sounds wonderful, I know. Alright, so the following table shows a random sample of 200 cyclists and the routes that they prefer to take when they're out cycling. So here we got gender, we got female and male. We also have a lake path, a hilly path, and a wooded path. And each of the cyclists falls in multiple of these little parts. Okay. So, instead of writing female and male and hilly path and lake, it's too much writing. We can just assign letters to the events. So for example, we can let F be female, M male, L lake path, H hill, and W wood. So that's what we'll do. That will save us some time and energy and other resources. So now we need to find 5 things. The probability of W not happening, probability of at least one male, probability of lake or male, probability of female and hilly path, and the probability of wooded path given that female has already happened. Alright, here we go. So the very first thing I would like to do is, like I mentioned, instead of writing all these long words and phrases and stuff, we'll just replace them with the letters that we assigned them. So female will be an F, male was an M, lake for L, H for hill, and W for wood. And the other important thing you should do first, whenever you see a table like this, just add up the columns and the rows. So for example, here we'll write the totals there. So we add 45 plus 38 plus a 27, we get a 110. And the 26 plus the 52 plus the 12, that'll give us a 90. And also, don't forget, add up the columns. So the 45 plus the 26, that's It's a 71. 38 and 52 is a 90. 27 and 12 is a 39. And then as a very final check, add up the totals and see if you get the same thing. So 110 and 90, that is 200. And 71 plus 90 plus 39 is also 200. So that way we can check if we added correctly. And there we go. Now this is the table that we're going to use to solve this. So the very first thing that we need to find is the probability of W not happening. So let's bring out our handy dandy formula. So this is a general formula, right? So the probability of event A not happening is 1 minus the probability of A happening. So let's apply that rule to our problem. So this is going to equal to 1 minus the probability of W happening. So then how do we find the probability of W? That's where we take a look at our chart. So right here is where we have all of the W information, right? So 27 of the cyclists who prefer the wooded path are female and 12 are male. But in total, they are 39. And the grand total of this chart, of this table, is 200. So the probability of randomly selecting one cyclist that prefers the wooded path here is 39 out of 200. Once we subtract 1 from this, then we get 161 out of 200. And like I mentioned before, you can leave it as an exact fraction, as simplified as possible, or you can use a decimal. In this case, a decimal is nice and neat. It stops right there. So yeah, I'll mostly use decimals. And there we go. That is the probability of W not happening. Nice. Let's keep going. The second thing that we needed to find was the probability of at least one occurrence of a male cyclist. So our at least one formula tells us that that is equal to 1 minus the probability of no A occurrences. So let's apply that here. So the probability of at least one male occurrence is equal to 1 minus the probability of no male occurrences. So we stop to think about it. Now we're talking about no male occurrences. So the only other option that could happen are that they're all female. Pretty neat, huh? So here, the total female cyclists we have is 110. And the grand total is still the 200. So the probability of picking no males or all females is 110 out of 200. And once we subtract 1 minus 110 over 200, we get a 90 over 200. We can simplify a bit more, have the 9 over 20, or we can also write it as a nice decimal, 0.45. And there we go. Third item on the list, the probability of L or M. So our general formula tells us that it's the probability of the first event plus probability of the second event, and we subtract the probability of both events happening at the exact same time. So let's rewrite this using our letters and our notation. So we have the probability of L plus the probability of M minus the probability of L and M. So let's find these probabilities using our chart. So first of all, we have L, which is right there. Those are all the cyclists that prefer the lake path. So 71 in total. And now, here we have all the male cyclists, which are 90 in total. But if we look closely, there is an overlap between the lake path and the male cyclist. It's right there on the 26. So those 26 cyclists are both male and prefer the like path at the exact same time. So that is the overlap that we are going to be subtracting. So the way we're going to write this is a 71 out of 200, which is the probability of the like path, plus the 90 over the 200, which are all the male cyclists. And we're going to subtract the 26 out of the 200 because they're both male cyclists and they prefer the like path. So that 26, we're basically counting it twice. So that's going to mess up our probabilities. So that is why we subtract. That gives us a 135 out of 200, which in essence, if we simplify, is 27 out of 40, or a 0.675. And there we go. That's the addition rule. Now, had our events not overlapped, so if they didn't cross at any point, we wouldn't have to subtract the overlap because, well, there is no overlap. So just be careful. Maybe the problem is going to ask you to find certain probability using the addition rule, and the events just happen to be disjoint. So there's no overlap that we need to subtract. So watch out for that. Item number 4, the probability of F and H. So our formal multiplication rule tells us that it's the probability of the first event times the probability of the second event, given that the first event has already happened. So let's write that down in our terms. It's probability of F times the probability of H, given F already happened. Cool, so now how do we find all these weird values in this table? So first of all, let's find the probability of F. So here we have all the female cyclists, 110 out of 200. Now, say that we take out one cyclist from this chart, right? So we take it out and we set them on the side. Cool, so keep that in mind. Now, the probability of the cyclists who prefer the hill path is right there. It's 90. However, F, or the female cyclist, has already happened. We took out that cyclist and put it outside of this chart. So now the grand total is no longer 200, but rather 199. So that's what the given F has already happened means. We randomly select one item or subject, we set it on the side, and now the grand total changes. So that is the main kind of weird thing that happens with the multiplication rule. So once we write these probabilities, it's the 110 out of 200. So that's the probability of selecting a female cyclist, times 90 out of 199. And just to recap, the 199 is because we already took one cyclist out and did not put it back in the chart. So once we multiply all that together, we get a 99 out of 398. This is already simplified, so that's why it looks weird. And this decimal is not so nice. It repeats and it's got a lot of numbers going on. We just round to 3 significant digits. So 0.249. And there we go. And the very last item here, the probability of W, given that F has already happened. Our formula tells us that it's the probability of both events at the same time divided by the first event that has already happened. So let's rewrite that over here. So this is the probability of F and W divided by the probability of F. Okay, so here we go. So the very first thing we need to find is the probability of F and W. So that's where they meet, or where they happen at the exact same time. So we need a cyclist that's a female and prefers the wooded path. And that value is right there. That's the 27. Those are the cyclists that are both female and prefer the wooded path. And the grand total is still 200, so 27 out of 200. Now, the probability of a female, well, is right there. The 110 total cyclists that are female. And the grand total is still 200. Now, what's going to happen here? Bam. We got a fraction over a fraction. So we have the 27 out of 200, which are the female cyclists who prefer the wooded path, and the 110 out of 200, which are all the female cyclists. So you may be wondering, man, this is way too complicated. It's a fraction over a fraction. I dislike fractions from the beginning. Now you're mixing them. Don't worry. What's really cool, both the fraction up top and at the bottom, they both have the exact same denominator. So a really neat thing we can do is kind of just get rid of them and just use their numerators. So all this mess turns into 27 out of 110. And that doesn't look so bad, huh? So now we use a calculator and we get a bunch of numbers, but we can round to 3. So 0.245. And there we go. Wasn't that fun? Wasn't that like energizing, doing a lot of math? Yes, it definitely is. There's no is not a correct answer. All right. The last topic we'll be covering in this video is counting. And you may be wondering, what do you mean by counting? I know how to count. It's 1, 2, 3, 4, 5. Partially what we mean by counting is arranging certain items in specific orders or in groups. There's very specific formulas that we use to determine this kind of counting. The very first rule here, the multiplication counting rule. This rule tells us that for a sequence of events in which the first event can occur in n one ways, and the one as a subscript is just to specify the event. The second event can occur in n two ways, and so on and so forth until we arrive to the very last event that can occur in n k ways. Then the total number of possible outcomes is n1 times n2, and then we just keep on multiplying however many ways the next events can occur until we reach the very last event, and it's different ways it can happen. So how do we use this rule? Let's try an example. Bartholomew has 5 pairs of shoes, 6 pairs of pants, 3 belts, 40 shirts, and 4 jackets. How many basic outfits can he put together? So our counting rule tells us that for certain events that can happen in different ways, we just multiply them all together. So in Bartholomew's case, he's got 5 pairs of shoes, so it'll be the first 5 that we write there. We multiply that by a 6, because that's how many different pairs of pants he's got, times 3, because of the 3 belts, times 40, times 4. So each kind of clothing item can happen in that many different ways, so we just multiply them all out, and Bartholomew can have 14,400 possible outfits. That is enough outfits to last them about almost 40 years if you were to wear one outfit each day. So yeah, if you repeat this little experiment with your wardrobe or your closet, pretty sure you'll also have enough outfits to last you a lifetime. Sure, construction boots, beach shorts, and a dress shirt doesn't go well in an outfit, but hey, they're unique outfits. So yeah, this is a neat little experiment you can try. The second rule is the factorial rule. So that's where we'll be using that big old exclamation mark right there. This rule tells us that for n different items, and when all n items are selected, the number of different arrangements is n factorial. And that's how we pronounce. So what is n factorial? N factorial is n, so it's the same number, multiplied by n minus 1. So that same number minus 1 times that same number minus 2. And then we just keep on multiplying down, down, down until we reach 3 times 2 times 1. The little formula or definition underneath n factorial equals n times n minus 1 factorial. That's what we call a recursive definition. We'll be using this little trick in one of the practice problems, so look forward to that. And by the special definition, 0 factorial is defined to be a 1. With this kind of problem, with the factorial, order is important. So keep that in mind. Now, let's see this rule in action. Crisostomo is eating Chinese food for dinner, and on his plate, he has 1 serving of each of the following dishes: beef and broccoli, chop suey, barbecue pork, fried rice, chow mein, and orange chicken. If he were to eat all these dishes one by one, without mixing any of them, in how many different orders could he eat his dinner? So in this case, Crisostomo has 6 dishes. And he's got the beef and broccoli, chop suey, that's 2, barbecue pork 3, fried rice 4, chow mein 5, orange chicken 6. So 6 total dishes on his plate. And he's gonna eat one by one. So he can start off with beef and broccoli, and then move on to barbecue pork, chow mein, until so on and so forth. Or he could start anywhere he wants, right? So fried rice, or he can start with orange chicken. So, in how many different orders can he eat his dinner? So we have n factorial. We're going to write as 6 factorial because we have 6 different dishes. And 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1. So we keep multiplying down, down, down until we reach 3, 2, 1. Once we do that, that will give us 720 possible orders that he can eat all those dishes one by one without mixing them. So that's a lot of different ways he can eat his dinner. Kind of craving Chinese food now. So multiplying is fine and dandy. It's not as complicated as the other things we've been doing. However, there's a quicker way to obtain these factorials using our calculator. So the first thing we can type in is the 6, because that's how we have the number there. Now to get the factorial, we need to jump over to math, which is right under the alpha key. And we'll head over to the prob, or probability window, or tab, or whatever it's called. And there it is. Option 4 will give us the factorial. So if we select that, we got 6 factorial. And now we just hit enter. And bam, 720. So that's much quicker than multiplying 6 times 5 times 4. So yes, you can use this as well. The third rule in counting is the Permutations Rule. This rule says for n different items, and when r of them are selected without replacement, the number of different permutations is given by the following formula. So NPR, we like to call that n pick r. So pick, P for pick. And that's equal to n factorial divided by n minus r, and then factorial. For the Permutations Rule, order is also important. And to illustrate this, we can have a look at this picture over here. We have this multiple ice cream scoops on a cone, right? The only logical way to eat all that tower of ice cream is to start from the top and head downwards. If we start at the vanilla one, the very first scoop there, we risk toppling the entire ice cream tower. So that wouldn't be nice. In fact, if we eat any ice cream scoop that has another scoop on top of it, we risk drop in the scoops above, right? So there's only one way to eat this, right on top, and then just downwards. So the order is important. Now let's see an example. Dolores has the same dinner as Crisostomo: beef and broccoli, chop suey, barbecue pork, fried rice, chow mein, and orange chicken. But she can't eat everything in one sitting. She can only eat 3 of the dishes, and she'll eat the leftovers tomorrow. In how many different orders could she eat her dinner if she ate the dishes one by one without mixing them? So now, similar to Crisostomo, we have those 6 same dishes, but Dolores is only going to pick 3 of them to eat that night. So we have 6 pick 3. So now we use our formula. We have 6 factorial up top, and then 6 minus 3 factorial on the bottom. 6 minus 3 will just give us a 3 factorial. And here's where we're going to use our neat little trick, our recursive definition. 6 factorial, we can break it down until we reach the 3, like this. We have the 6 times the 5 times the 4 times the 3 factorial. So we just stop right there at the 3 factorial. That allows us to just simplify the 3 factorials on both the top and the bottom, leaving us with 6 times 5 times 4, which is equal to 120 possible orders. So yeah, much less orders than Crisostomo, but still just as tasty because it's still Chinese food. And if you're wondering, I do eat my Chinese food one dish at a time. Sometimes when I'm feeling funky, I'll mix some of them around, but usually not. In the factorial example, once I showed you how to use a calculator, you may have noticed that we also have a p there. And that's exactly what we're going to use to find this permutation using the calculator. If we head over to the math key once more, to the probability tab, we can see that option 2 has an n pick r option. That's the one we're going to choose. Press a 2. So our n is a 6. Our r is a 3. Once we have that typed in, we just hit an enter. And out comes a 120. So you can also use this little calculator thing to quickly work out a permutation. That's pretty neat. There's an extension for the Permutations Rule. That happens when we have identical items. So this other specific rule tells us, for n items, and when all n of them are selected without replacement, but some of the items are identical to others, the number of different permutations is found as follows: n factorial divided by n1 factorial, so the first item that is repeated, times n2 factorial, the second item that's repeated, and then we just keep on multiplying down until we have the very last item that repeats, also factorial, so nk factorial. And here order is still important. A little example here on the picture. Let's say that we're trying to arrange all those markers in different ways, but we have 4 of each color. We got 4 reds, 4 blues, 4 of each color. So that's where we would have to use this rule here, because we have multiple identical items. All right, so let's see. Esmeralda randomly asks herself one day, in how many ways can I arrange the word Mississippi? Her mind cannot get rid of this doubt, and she must resolve it in order to achieve inner peace. So let's help Esmeralda out, right? The first thing we need to find is how many total letters we're working with, and how many of them repeat, and how many times they repeat. So, Mississippi, the word has 11 total letters. So our main N is 11. So of those 11 words, M appears once. So the number of times N happens is 1. So NM is 1. Since N doesn't repeat, we can basically disregard it, but we'll just include it for continuity's sake. Alright, now I appears 4 times. So NI is 4. S appears 4 times as well. So NS is also 4. And P appears twice. So NP is 2. So here is how our little formula looks. We got n factorial up top, and on the bottom we have all the letters, and followed by the factorial. So now we substitute these values. We're going to have 11 factorial over 1 factorial times 4 factorial times another 4 factorial times the 2 factorial. So here, I kind of skipped doing the recursive definition little trick, because I just wanted to get through this problem. So 11 factorial turns into all of that. The denominator turns into all of that. And the very final answer is 34,650 possible arrangements. And that is a lot of arrangements. So now Esmeralda knows the answer to her doubt, and now she can sleep in peace. So yeah, we did it, everyone. We helped her. With the identical items permutations rule here, there isn't a specific calculator key or command that will help us find this automatically. We're gonna have to type it all ourselves. But I did want to show you how to do this on this specific calculator, because what I didn't know when I was taking this class is that you could input fractions into a Texas calculator. To do this, you just hit the alpha key, and then you go up to the Y equals button, and green will have the F1. So once we choose that, it will bring up this little calculator tab. And option 1 allows us to just, bam, work with a fraction, which is really cool. So now in this fraction, we can type in all the stuff that we have. The 11 factorial. There it is. And then at the bottom, we can type in all that stuff. The 1 factorial is 1, so it's not really going to change anything, but I'll include it just for consistency. So we got the 1 factorial times a 4 factorial times another 4 factorial times a 2 factorial. Once we have all that typed in, we can just hit an enter, and there we go, 34,650. So yeah, calculators, the Texas calculators with fractions, that is awesome. So hopefully this will be able to help you out. The very last rule in counting is Combinations Rule. This rule states that for n different items, and when r of them are selected without replacement, the number of different combinations is given by this formula. So NCR. The way we like to read this is N choose R, so C for choose. This second parentheses looking thing, that's how the NCR is written in further mathematics. So upwards in number theory or other weird stuff, that's how it's written. So if you are taking further math classes up in a university level, this is what they mean, and this is how it looks like. So the formula is n factorial over r factorial times n minus r factorial. And what's really big about combinations is that order is not important. In the picture, we have a bowl of ice cream, right? So here, we can eat that ice cream any way we want, because we aren't risking toppling any scoops and dropping them on the floor, right? And if we were to spin the bowl as many times as we want, it's still going to be the same combination of ice cream. So that's kind of a neat way to tell the difference between a permutation or a combination. For permutations, order is super important. Every single order is unique. For combinations, we're focusing more on groups and not so much the orders. So how many ways can we group certain items together? And everybody loves ice cream, so I think it's a good way to remember and tell the difference between those two. Alright, so let's try one last example. Freya wants to play a 4-player online game with some of her friends. However, she has 15 close friends to choose from. How many different groups of 3 friends can she invite to play online? So the game is a 4-player game, but Freya herself is going to be one of them. So she needs 3 more to complete the full campaign. So here we're choosing the combinations because the order in which she invites her friends doesn't really matter. It's just that same group of 4 playing the game together, right? So she's got 15 friends to choose from, and she's going to be picking 3. So if we use the formula, it's going to look like this. 15 factorial over 3 factorial times 15 minus 3 factorial. So if we do a little bit of simplifying, 3 factorial turns into a 6, and 15 minus 3 turns into a 12, and we've got that factorial there. So once more, if we do our cool little recursive definition trick, we're gonna break down the 15 factorial down to a 12 factorial, like this. And then that allows us to just simplify the 12 factorials out. And if we do a bit of multiplying, 15 times 14 times 13 is 2,730 divided by 6 finally results in 455 different groups of 3 friends that she can invite to play online. And there we go. That was pretty fun. Yeah. And last but not least, we can also work out a combination problem with our calculator. It's very similar to the permutation one, it's just a different option in the calculator. We head over to the math key, to the prob tab, and it's option number 3, and choose R. We select that, we got a 15 as our N, and we're choosing 3 from this group of 15. And once we have that typed in, press and enter, and there we go. 455 possible outcomes. So this is the quickest way to work out a combination and permutation and factorial. So the calculator once more will be a very helpful tool for us. So that about wraps it up for this video. It was pretty fun. Now for the next video, we're going to still be working a bit with probability, but now we're going to be expanding upon probabilities and the rules of probabilities. Namely, we'll be taking a look at probability distributions. So we'll have a lot of fun with the binomial probability distribution as well. So yeah, I look forward to working with you guys on this stuff. Okay, so once more, thanks for your attention, and I will see you next time.